Hello friends, in this video today we are going to discuss about constraints. Okay, uh, what do you mean by constraints? So here you see, suppose this is a particle, or you can consider a system of particles. Let me consider a particle here. So suppose it can move in all direction, in this direction, that direction, that direction, that direction, in space. It is in space, there is no limit, no boundary. Okay, it can move everywhere. Suppose now I have suppose it is this particle is enclosed in a container. Suppose now there is a restriction in its motion. There is restriction in its motion. So it cannot go beyond the walls of this box. Okay. So suppose if R represent the distance covered by this particle, and L is the dimension, LB is the dimension of the suppose box, then this R will be always less than equal to L, always less than equal to B, and always less than equal to H. Okay, because it cannot go beyond this beyond the walls of this box, then such kind of motions are called constraint motions, and these conditions are known as constraints. So how we can define constraints? So we can say constraints are the restrictions. We can say constraints are the restrictions imposed on the motion of a system of particles. Okay. Now you see, suppose we have let us take another example. Suppose this is a simple pendulum, so it can oscillate in this way. So here you see, at all the time this length will be fixed. This length will be fixed. Okay, this is L, suppose. Okay, and now position vector will be suppose R. Okay, so we can by Cartesian coordinate we can write the constraint equation as x square plus y square is equal to L square. Okay, so here you see, as it is not dependent on time, so in each and every time, each and every instant, this L is fixed. It is always going to be constant, and it is not depends on time. It doesn't vary with time. Okay, and here why it is constant equation, because you see this mass of this pendulum cannot go beyond this because it is attached to this string, and length of the string is L, and so it cannot leave this system. So this is also a constraint, and it is suppose allowed to oscillate in a plane. Suppose this is the plane, this is suppose xy plane. Okay, so this is x, suppose this is y coordinate, this is xy plane. Okay, then the constraint equation is given by this. Okay, so it is not depend on time. In such kind of constraints are known as Scleronomic constant. Okay, so this is called Scleronomic constant. Let me write the definition here. So Scleronomic constraint. So what is the definition of this type of constraint? If constraint relations are are not or independent, or you can say independent of time, independent of time, then such constraint such constraints are Scleronomic. Scleronomic constraint. For example, we can write the simple pendulum, or we can say case of rigid body. Okay, motion of rigid body, case of rigid body. Rigid body. Suppose we have a rigid body. This is a rigid body. Suppose if you consider any 2 points of this body, so it is allowed to move. Now you see, if it is allowed to move, this object is moving. Okay, but here you see, doesn't matter it is moving or at rest, this distance between these two particles is always fixed. This is not going to change. It is not going to be changed with time. Okay, so it is independent of time. Now if the constraints depends on time, then we will say the constraint is rheonomic. Okay, rheonomic constraints. So if constraints relations are relations depend on time, then the constraint is rheonomic. Okay, so hope you have understood this, what is rheonomic and what is Scleronomic constraints. So suppose, let me take an example here. Suppose we have compressible body, or let me take the example of a pendulum of variable length. Suppose this is a string and this is suppose rigid, and another suppose this is a rod and another rod is joined here, so that here you see at this point, and they can that means they are not fixed like this as a straight, they can change their position like this. Okay, so this rod can rotate, this can oscillate about this point, and this rod can oscillate about this point where they are joined with each other. Okay, so such kind of pendulum. Suppose here is the mass of this pendulum. Now here you see this position with respect to this origin O, this position will change with time. This R is going to be changed with time. Okay, so this is a length of the length, total length is suppose L. If you consider here, R is the function of time here, and this is going to be, this is going to vary with time. Okay, sometime it may take this position, this is the mass, or sometime it may take this position here, this are the two rods, then it will be longer, then this distance is shorter. So this is going to be keep changing. Okay, this is going to vary all the time with time. So this is a function of time. So we can say it is rheonomic constraint. Okay, so here we can give example. Example, deformable bodies. Okay, deformable means which is not rigid. Suppose we have an object here deformable, so it changes its shape with time. Suppose if the shape of the object changes with time, then suppose if you consider 2 points of this object, and if it changes its shape like this, then the distance between these 2 points changes. Distance is not fixed here, it changes with time. So this such kind of motion constraint also rheonomic. Okay, so now let's come to holonomic. So holonomic constraint. So holonomic, if the constraint relations are independent of velocity, then such constraint is called holonomic. For example, suppose cylinder rolling without sliding down an inclined plane. Without sliding or without slipping, without sliding down a inclined plane. Inclined plane. This is holonomic, example of holonomic. So let me scroll down the page. You can take the condition of pendulum also, case of pendulum. This is also holonomic, okay, because the relation here you see x square plus y square is equal to L square. This is the length L. This also doesn't contain any velocity term, so that's why it is also holonomic. Now non-holonomic. Non-holonomic constant. Now you see, if non-holonomic constants, here you say if the constraint relations are functions of here say okay, let me write here irreducible function, not only function. Functions of velocities. Then the constraint is non-holonomic. For example, sphere rolling without sliding. Down an inclined plane, okay, right here, inclined plane, okay. So I have done a mistake here, here this inclined, okay, inclined plane. So now you see, in these two cases, in the first case, so constant relations, they are function of velocity here, in holonomic constant, that depends on velocity, sorry, that doesn't independent of velocity, and here in this case function of velocity, okay, irreducible functions of velocity, that means they depends on velocities. Now you see, here we have taken as an example here cylinder rolling without sliding down an inclined plane, and here we have taken sphere rolling without sliding down an inclined plane. So in these two cases, here you see, suppose this is an sphere, sorry, not a sphere, cylinder. So if it is rolling down an inclined plane, and here is the axis of rotation here, so this is the initial point. So now it is rolling in this direction in an inclined plane. So at this position, this is the axis, so this is R, and the angle of rotation here, this so this is theta, suppose, and here you see, so let me draw it clearly, okay. Suppose this is the cylinder and this is the radius R, okay, this is the radius R, and this is an inclined plane, suppose it is rolling on an inclined plane. So at this position, suppose here this angle, this is r, this angle is suppose theta from this position, so this is the angle, so this is the initial position of this radius, and here it is rotates through theta, this angle is theta suppose, and this is the axis here. So let me be clear. Okay, so this was the radius here initially, and this is the angle theta, this is the initial position, this is theta, so it is rotating rolling in this direction, this is r. Okay, and from this position to this, the distance between these two positions, this is suppose r. Okay, then in this case this s is equal to s dot, this is linear velocity, is equal to r theta dot. Okay, theta dot. If there is no sliding, okay, so which also can be written as s dot minus r theta dot is equal to 0. So dot means here you can write this one as dot means ds by dt, you can write here, and d theta by dt. So if you integrate this, then you will get s minus r theta is equal to constant. So here you see this velocity is reducible. Okay, it is independent of velocity. Now there is no longer velocity term in this relation, so that's why this condition is holonomic. But in case of sphere rolling down an inclined plane, the angular velocity, and this cannot be, here you see this cannot be represented in this term d theta by dt, so it cannot be expressed in this way. And here this omega is generally not expressible in the form of total time derivative of any single coordinate, and so it is non-integrable. So here we cannot integrate here, it cannot be integrated or reduced. So that's why this is the sphere rolling down an inclined plane is non-holonomic. Okay, now now bilateral constraint. So what do you mean by bilateral constraint? Now you see, if constraint relations are in the form of equation, okay, if constraint relations are in the form of equation, then the constraint is called bilateral constraint. So we can take the example of simple pendulum here also. Okay, simple pendulum. So in case of simple pendulum, we used to write the constraint relation as x square plus y square. If the mass is along xy direction, on xy plane, this is on xy plane, then this is the length L, then by this equation we used to represent the constraint here. So this is an equation, this constraint relation is in equation, so that's why it is bilateral. Okay, so now what is unilateral? Now another type, there is another type, unilateral constraint. So here you see, if constant relations are inequalities, then the constraint is unilateral. For example, motion of gas molecule within the container. In a container, suppose this is a container, this is the particle, okay, this is the particle, and its position vector is suppose r, and it always suppose it is a cuboidal box of dimension L, then it is always going to be less than equal to L. So it is a relation, inequality relation. So in such type of constraint are known as unilateral. Hope you have understood this. Now let's move on to another type. Okay, so now conservative. Constraint. So suppose we have a system and where total mechanical energy of the system is conserved, suppose, okay. If the forces of constraint do not do any work and total mechanical energy of the system is conserved, okay, while performing the constant motion. If the total mechanical energy is conserved while energy of the system is conserved while performing constraint motion. Then that constraint is conservative. For example, here also we can give the example of pendulum, okay, or any rigid body, because in case of rigid body total energy conserved, okay. So let me take the example of simple pendulum. With rigid support. So suppose this is the pendulum here, and while oscillating, tension acting on it is suppose T, and so R be the position vector, then total work done is given by T by del R. Here in this case it is not a function of T, that's why del R will be 0, that's why total energy will be 0. So as total energy is conserved, so it is conservative. So if you take the example of the pendulum, where this length is not fixed, this length is not fixed, so of variable length in this case. So in this case, so del r is not equal to 0, okay, as it is function of time. So that's why in that case W is also not equal to 0, work done is also not equal to 0. So that will be dissipative constraint. So let me write the definition here. Dissipative constraint. So if the total energy, total mechanical energy of the system is not conserved, while performing constraint motion, then the constraint is dissipative. Example, pendulum of variable length, okay, with variable length. So this is all about constraints. So in the next topic we will discuss about generalized, in the next video we are going to discuss about generalized coordinates, and also we are going to discuss about degrees of freedom. Okay, so thank you for watching. If you like it, if you are new to my channel, subscribe the channel and share with your friends, and see you soon. Thank you.